here's the test circuit that we're working with. You can see it's the same as what we did on the simulator. I have a 1 k ohm resistor here. I have a 1 microfarad non-polarized capacitor here. And I have the signal generator leads coming in here, the active lead to the top of the capacitor. So in this case, I'm actually measuring across the resistor, and with this other channel of the oscilloscope, I'm measuring the voltage being supplied from the signal generator. And of course, we had that set for 2 volts peak, which is 4 volts peak to peak, coming into the oscilloscope channel A, and this is channel B. I've got the Rigol oscilloscope set up here. You can see that I've got the 2 waveforms. Channel 1 is this yellow colour, channel 2 is the blue. And I've used the cursors on the screen to show me that I've got a time difference between the 2 waveforms of 248 microseconds. Now I'll go quickly through the steps how I was able to do that quite accurately by stretching the pattern out on the screen. I have done this with some other videos though, so I won't waste too much time on it. Essentially, look, I'll just turn the time per division back down, and if you imagine, you can see here that there is a phase difference between the 2 waveforms, but trying to get any sort of a decent time comparison there is just too hard. So the best way is to stretch the screen out a little bit, and we have to make sure that both the channels are centered here. So there's an actual detent position there, so it's pretty easy to make sure that they're both centered. And with the cursor control here, it's not too hard to be able to select which cursor we want. Cursor A has been selected, and while we're in the manual mode, I can move it to put it over the top of the falling part of the waveform, and then deselect cursor A, select cursor B, and then I can move cursor B as well. Sometimes it's a good idea to increase the gain on each channel, whoops, and like that. And now you can see that that cursor was probably slightly in the wrong spot. So back to that cursor again. Cursor, make sure it's manual. Cursor A, I can put him right over where he's supposed to be, and cursor B, I can move to there. And look, I had 248 microseconds before, now it's telling me I've got 240 microseconds, so I guess we could probably even average that. I'd be happy with about 244 microseconds time delay from channel 1 to channel 2. I've now turned the circuit around so that I'm measuring the output voltage now across the resistor, and you can see that the time difference between the 2 waveforms is much smaller. So let's do similar to what we did on the previous pattern where I was measuring across the capacitor and got that quite large time difference. Let's just stretch this out and see if we can make things a little bit more easy to work with. Using the horizontal control on the oscilloscope, just moving that along. I've got 2 rising sections of the waveform here. I've guaranteed that they're both centered on the middle of the oscilloscope screen, and then using the cursor control, moving one cursor along. We might just even increase the gain on each vertical channel there. Moving the cursor along again, cursor control, and then the other cursor. Move him along to there, and we can get a fairly accurate reading there of 30 microseconds time difference between channel 1 and channel 2. So now we had 244 microseconds of time difference before. We've got 30 microseconds of time difference now. We've got 1.11 milliseconds of total period at 900 Hertz. So it's time to do some quick mathematics on those 2 figures. So just to recap what we've done here in the video, we had 900 hertz of frequency coming in from the signal generator, which works out to be 1.11 milliseconds, period. That's 1 divided by 900 hertz. Series circuit with 1 k-ohm resistance, 1 microfarad of capacitance. And at one point we have to transpose these components in the circuit so that we have, to start with, the capacitor in shunt, and then later the resistor in shunt with the output, so that we can measure VC, or when we move the resistor to the output, we can measure VR. Based on the 900 hertz and finding XC, which is 1 on omega C, 1 on 2 pi FC, that is, 177 ohms. And then using the polar function on the calculator, pole 1K, 177 to get the impedance of 1015 ohms at an angle of 10.03, which is going to be the supply voltage from the signal generator lagging the voltage across the resistance in the circuit. We've done this and we've set it up on the oscilloscope, and we've taken some time delay readings, and we got 244 microseconds time delay when we had the capacitor in shunt. That gave us 79 degrees. And then with the resistor in shunt, we got 30 microseconds. And of course, we have to, in each case, divide it by the total period of the waveform, which is 1.11 milliseconds, multiplied by 360 degrees to get the angle 10 degrees. Ideally, if the readings were really super accurate, they'd add up to exactly 90 degrees. We haven't done too bad. We've got 89 degrees. So we end up with 10 degrees of phase shift in the circuit here. And we've got, of course, 80 degrees in round terms between the supply voltage, which is leading the voltage across the capacitance in the circuit. So that pretty well wraps it up, and that's exactly in line with what we did in the theory in class using the circuit simulator. But in this case, it was using the Rigol oscilloscope and using actual components to do the job and prove that it all works out exactly in line with our theory.